Okay, well, I think we'll get started. Could I just quickly get someone to confirm the chat that they can hear me okay?
You're loud and clear.
Lovely. Perfect. Okay, so hi everyone, welcome to this webinar on Python on ARCHER2. So I've sort of aimed this webinar at two groups of people who use Python and want to know how to start using it on ARCHER2, and also people who might be interested in what Python can do for their work on ARCHER2. So there'll be a little bit of background on both those things, and so hopefully everyone will find something useful out of it. So just a quick overview, I'll give some background on Python itself and some useful modules that are provided, in particular ones that are provided as standard on ARCHER2. I'll talk a bit about parallelism in Python and some of the ways to do that, as well as some of the difficulties with it. I'll talk a bit about Python specifically on ARCHER2 and some of the things you have to do to get yourself set up. Running Python on the ARCHER2 login nodes and running Python on the compute nodes, which work slightly differently. And then also a bit about managing your Python environment. Okay, so firstly, why do people want to use Python in general? So firstly, it's a very common language for people to learn as a sort of intro to programming. It's easy to write simple and readable code, and it's also easy to do so very quickly. It's a free and open source language, so anyone can use it. It's very well supported on in any environment, so there are very low barriers to entry. It also supports many different programming styles, whether you prefer programming in an object-oriented, imperative, or functional programming. Python supports them all, and also doesn't require that you use any particular style of programming. So it's very open in that sense. And also provides many different useful scientific libraries. So there are a lot of useful functions there that you don't need to do yourself that are already provided for you in these libraries. Some common uses for Python. So analyzing data, whether that be creating plots or graphs of your data or running statistical analysis on them. There is generally a Python library that can do what you're looking for. Rapid testing. So this is because, as I mentioned earlier, it's easy to write code very quickly in Python, and one common thing to do is to write prototype algorithms or functions in Python, just to as a sanity test to check that they work properly before moving on to maybe a more efficient but slower language to write in. Gluing together C and Fortran programs, so there are interfaces between Python and both C and Fortran, so that you can call C and Fortran functions to do the bits of number crunching that require some heavy lifting, while the Python just sort of ties it all together. And lastly, writing full programs. This comes with a little bit of a caveat because Python is not Python programs are not very fast. They're often quite slow. There are a number of reasons because of this, some of which I'll go into. But sometimes it's for some of the benefits of Python we mentioned above. Sometimes it is a good justification to write full programs in Python, but often you're better off using a faster language like C or Fortran. Okay, just a bit more background. So Python is an interpreted language, as in essentially not a compiled language. So instead of compiling your source code into machine code and then running that executable, you feed your code directly into the Python interpreter. There are two ways to do this. The first is to create a script file that you pass to the interpreter, which then executes it, or you can run the interpreter without a script file, and that starts an interactive Python environment where you can input your code line by line. So this is an example of the first option with a script file. We have a file here called helloworld.py, which just contains print hello world. And if we run python helloworld.py, we get hello world out. And then we have the second option, which is just to run the interpreter without a script file. And that opens up an interactive session. And if we type print hello world into that, we again get hello world. So on ARCHER2, it's recommended that you use the HV Cray Python distribution, which is the one that's provided on both the login and compute nodes. I'll go into more detail later about how you use that specific distribution. It provides Python 3, but not Python 2. And it's important to note that Python 3 is not backwards compatible with Python 2. There are a number of things that don't work. The print function changing is probably the most well-known one, but there are a number of things that don't work. Also, in general, if you need to contact the service desk with queries about your Python code, it is generally easier for us to provide support for Python 3 codes because that's what we support on ARCHER2. There are also a number of useful packages that are provided in this distribution, all of which I'll go into more detail on in a couple of minutes. But we have Numpy, SciPy, MPI for Pi, and Dasc, and I'll go into more detail on those now. So Numpy is, and just to be clear, when I'm talking about these, I'm going to be giving a very brief overview of what each of these libraries provide. They all provide things in much more depth than what I'm about to go into, but this is just intended to give an overview of their main uses. So Numpy adds support for large multi-dimensional arrays. One of the issues that people often run into with Python is that it doesn't provide by default any arrays. Python uses lists instead, and lists often have performance issues. This is largely because of their flexibility. Lists in Python can contain any sort of mix of data types. You can have a list that includes a float, an integer, a string, and some other Python object, and that's all perfectly fine. But it means that whenever you want to do any sort of computationally intensive manipulation of these arrays, then it can take a very long time. But Numpy provides these array objects, as well as also a lot of functions to manipulate those arrays. So these are just a few examples of Numpy arrays and how they work. So in this first one here, we set A into as an array of A range 10, which gives the numbers from 0 up to 10, so from 0 to 9. We can do things like we can take a one-dimensional array and reshape it into a two-dimensional array, as seen here. So it takes a 1 by 10 array and turns it into a 2 by 5. And we also have things that provide distributions. So in this one, when we pass 1, 10, and 4, what that means is it provides 4 numbers equally spaced, starting at 1 and ending at 10. So we get 1, 4, 7, and 10. Then going back to the multi-dimensional array that we just have, here are some of the simple functions that you can execute on it, or the methods that you can call on these arrays. Summing over the 0th axis essentially means summing over columns. So you can see here that it's taken all the columns and I put it a sum for each of them, so 5, 7, 9, 11, 13. And another example is a cumulative sum over the other axis. So the first example was summing over rows. This one is summing over, summing over columns. This one is summing over rows, and doing so cumulatively. So adding on to the previous sum. The second example was SciPy. So SciPy builds on top of Numpy and adds basically a whole load of extra algorithms and functions that might be useful for scientific computing. These include fast Fourier transforms, linear algebra, signal processing, and some statistical packages. And it also includes other useful packages like pandas and matplotlib. Okay, MPI for Pi. So MPI for Pi is the Python version of the message passing interface, or MPI. So what MPI is designed for is for providing parallelism distributed memory systems, so where the different processors don't have access to each other's memory. And essentially the parallelism is provided by different processors working on different computational tasks, and with then occasional communication tasks between them, or messages that need to be passed. So MPI supports point-to-point communication. So that's when a single processor needs to communicate with a single other processor. Custom communication group topologies. So this essentially lets you create the concept of processors having neighbors and to be able to pass information easily between those neighbors. So this could be a Cartesian grid or a complex graph, but you have the ability to customize that however you will. Parallel I/O. So instead of needing to gather all of your data onto one processor, which might be prohibited by your memory limits, you can also do parallel I/O instead, which essentially means that all your processors will be writing to the same file simultaneously and potentially providing a lot of performance benefits. And also one-sided communication, which is essentially where processors read and write directly from each other's memory. So here's a quick example of MPI for Pi. And in this example, you can show that you can easily send things like NumPy arrays. So we have a communicator, which in this case is MPI ComWorld, which is just the set of all processors that are running the code. Then each processor can get their rank from within that communicator. So the ranks will be distributed from 0 up to the number of processors there are in the communicator -1. Then we can say if your rank equals 0, you can create. If the rank equals 0, you create this NumPy array called data, which contains 100 integers. And apologies, that second line com.send should be indented. But this sends that data to the destination with rank equals 1. And then on the other side, we have rank 1 create an empty array, and then it receives data from rank 0 into that array. So one thing you might note with this, if you are familiar with MPI, is that you don't actually have to specify what the data type is for this communication. It uses Python's loose typing to essentially work out what the data type is. But yes, so that's a simple example of some MPI routines that can be used. But if you have any experience with MPI on C or Fortran, you'll find that you can use it in much the same way using Python. So lastly, we have Dasc. So Dasc is a parallel computing library which sounds similar to MPI for Pi, but it works in a very different way. So first of all, it provides data collections that are designed to be used in parallel. So these can be parallel arrays or data frames that are designed to be distributed across lots of processors or threads. And it also contains schedulers which build task graphs. So a task graph essentially is building a list of dependencies between different functions or routines in your code. It can then use that to work out which ones can be done independently of one another and can therefore be done on different processes. So yes, these can be distributed across a cluster like ARCHER2, or if you were using this on your laptop, you could distribute them across threads on a single core. So a quick example of how Dasc works. So let's say we have these three very simple functions, double, triple, and add, which double and triple just double and triple the input respectively, and add takes two inputs and adds them together. So if we say, if we feed double and triple with 2, and then z with the output of double and triple, then we end up with the answer 10, assuming I've done my maths right. So this is fine, but x and the calculation of x and the calculation of y here don't depend on one another. So while this calculation, the calculation of x will have completely finished before the calculation of y has begun, we could actually do them simultaneously. And here's how Dasc accomplishes that. So Dasc use the sort of, I guess, bread and butter way of using Dasc is to use the delayed functions. So you can mark certain functions as being delayed, which essentially means that when the interpreter gets them, it doesn't immediately execute them. It just adds them to the task graph that it's building and then executes them all later. So after marking these functions as delayed, we run the same thing again. We run double the calculation for x, y, and z. And then if we investigate what z is at the moment, we don't get 10 anymore. We get a delayed object. And then if we call z.compute, then we get the answer 10. So so what's happening here is that as I said before, the calculation isn't actually done when you write z equals add x and y. You write all the functions that you want to happen first. They get built into a graph, and then only when compute is called is the actual calculation done. So this isn't particularly useful in this example because going to the trouble of building a graph is wasting far more time than it would have taken just to calculate x, y, and z from the beginning. But if you consider replacing these functions with much more computationally intensive ones, say that take an hour each to run, then it becomes obvious that you would much rather the calculation of x and y happen simultaneously on different processors than to have to do them sequentially. Okay, so I just want to talk a little bit about a thing called the global interpreter lock, which may be something that you've come across before if you use Python, and it's particularly pertinent because there are essentially two main ways of parallelizing code. One is to use something like MPI to pass messages between different processors on a distributed memory system, and the other is to use multi-threading. However, there's a bit of a problem with multi-threading when it comes to Python, because there's a global interpreter lock which prevents multiple threads from executing Python bytecode simultaneously. So what this means is that it's essentially there to prevent race conditions in the Python interpreter. So say if two threads try to increment a variable at the same time, they can get in each other's way, and if the timing of when they read and write from to memory gets mixed up, they can get in each other's way, and you can end up just having incorrect output from your code. So the purpose of the global interpreter lock is to ensure the thread safety of the Python interpreter. So basically to ensure those race conditions don't happen. But this does make thread-based parallelism difficult, because quite a lot of things that there are quite a lot of things you want to have done on different threads, but they can't access the bytecode simultaneously, so you're unable to. There are some ways that you can get around this. There are some operations that happen outside the global interpreter lock, so you can do parallel I/O on multiple threads. You can also, in general, operate on numerical data safely, but some things like pure Python objects, like strings or dictionary entries, I believe, cannot be multi-threaded because of this global interpreter lock. Okay, so coming to ARCHER2 and running Python on the front end or login nodes. So the first thing you want to do for running any Python code is running this command, module load cray Python, and that loads the HPE cray Python distribution that I talked about earlier. So this allows you to use either run interactive sessions or using Python script files. Also, if you have been running things on ARCHER2 before, you've probably had this said to you before, but it does bear repeating. Make sure that you only run short jobs on the front end. If you start running anything particularly intensive, then it will slow down the login nodes for other users, and quite likely what will happen is the systems team will shut your job down and send you an email asking you not to do it again. So yes, make sure to load the cray Python module. If you check which Python you're using on login before you load it, you'll see you're using the system Python, which is located in user bin Python. But if you load the cray Python module first and then run it again, you'll see you get a different version of Python. So make sure you're running the second one. It has all the packages and libraries built into it that you mentioned earlier. And also, if you are contacting the service desk for help, they will probably assume that you were using this version of Python. So in submission scripts, so here's just an example of a submission script to run on the compute nodes. So I'll assume I won't go through this in too much detail, because I sort of assume that most people who will be attending this will have some sort of experience of running things on Python or on ARCHER2. But this is an example of a submission for serial code. So one node, one task per node, one CPU per task. You would need to put in your own budget code there. You also need to make sure to use module load EPCC job environment. That really you should do on any code you're submitting to ARCHER2. It essentially sets up all the environment variables and paths correctly. You need to load the Python module. That's not just for doing on the login node. You'll need to do this in all your submission scripts that run on the back end. And then simply run your Python program. Here's an example of running a parallel script. So this is an example of one that uses MPI for Pi. Similar to the previous submission script, except we're now using 2 tasks per node instead of 1. Everything else is the same. The only important difference is that if you see the bottom line, it's no longer just Python followed by the Python script. It's srun Python. So srun is the the parallel job launcher used by Slurm, which is the workload manager on ARCHER2. And you need to make sure you wrap your Python calls with srun if you're using MPI for Pi or anything similar. Otherwise, what usually happens is it breaks with some sort of segfault or something. So so yes, make sure you're using srun and not just Python. So there are many packages provided with the distribution on ARCHER2, but you may want to install your own. The easiest way to do this is to use pip. So pip is pretty commonly used, so some of you may have a lot of experience using it already. One of the catches, however, on Archer is that by default, it installs packages in .local, which is on the home file system. So ARCHER2 has two file systems, home and work. Home and work can both be seen from the login nodes, but only work can be seen from the compute nodes. So if your submission script contains any reference to files that are located on the home file system, then they won't work properly on the compute nodes. So in order to make sure that they can be seen properly on the compute nodes, you need to change the variable Python user base, and you need to point that to somewhere in your in your user directory in /work. So in this example, T01 would be whatever your project code is, and then a user should be your username. You then need to add that path to your system path so that it can so that basically the packages that you install can be found. And yeah, the simplest way to do this is to add these two commands, the two exports, to your .bash rc, and if you do that, they'll be run on login, and you essentially never need to worry about them again. And then once you've done all that, you can use pip install /user followed by the package name in order to install extra packages. The reason you have to use the user flag is that by default it will install in a directory which requires root access, which you obviously won't have on ARCHER2. So this tells it that it's installing it for a user, and it will look to install it in the Python user base directory that you specified before. So if you one other method you might have used to manage your environment is to use Conda. Oh, sorry, yeah, I see there's a question in the chat. Yeah, I'm going to assume that was about this. Yes, you can use pip to install packages, but some of you may be more used to Conda. Conda and pip are sort of sometimes regarded as two different ways of doing the same thing, but they're not quite the same. Pip is used for installing Python packages, Python packages in whatever environment you happen to be working in, whereas Conda is for installing any sort of package in a Conda environment, which is a virtual environment that you create. So if all you're doing is installing Python packages in a Conda environment, then they're pretty similar. But if not, you may want to look in which one is best for you. The way to do this on ARCHER2 is to create your own Miniconda installation. I haven't gone into detail on this, but if you search for Miniconda online, you'll find plenty of documentation about how to download the installer, and from that it's essentially a matter of using conda install and then the package name. This also allows you to choose the version of Python you want. As far as I'm aware, there isn't a convenient way to do this using pip, and you're stuck with the version of Python that you're using. But for Conda, you can download installers for any version of Python that you happen to want to use. So if you need an older version for some sort of compatibility reason, then that might be the way to go for you. And lastly, just some useful links. So if you're having trouble with any of this, here's the link to the ARCHER2 service desk, who will be happy to answer any queries about this. And as well, some of the things I've talked about here are documented in the ARCHER2 documentation. I'll just post this in the chat as well, in case anyone wants a link they can click on. Yeah, so that contains quite a lot of the information I've talked about here. So yeah, that was the end of everything I had to say. So if anyone has any questions, either I or someone, some of my helpers in the chat will be happy to answer them.
Thanks very much, Caoimhín, for that nice overview of Python on ARCHER2. As Caoimhín said, if anyone has any questions, please feel free to ask them in the chat. I see Andrew Sunderland has a question. The question being, how does Numpy SciPy performance compare to, for example, libsci or
The answer to that, I don't know offhand. I suspect that Andy is.
I can say something if you want, Caoimhín. So the Numpy SciPy are built on top of Cray libsci, right? Which provides BLAS, LAPACK, various libraries like that. So I guess there would be some overhead for calling it from Python, but in the same way that, you know, if you use Conda, the NumPy is built on top of MKL. It's exactly the Intel's MKL. Generally, it's exactly the same sort of thing. So the way you get the performance is from NumPy SciPy is just calling down to libsci in terms of the Cray Python environment anyway. If you installed your own NumPy SciPy through Conda, it would generally come with one of the latest versions of Intel's MKL. Now, of course, because ARCHER2 has AMD processors, the MKL library does not, at the moment, give best performance on the processors. In the old versions of MKL, 2019 and before, you could set a hidden environment variable that would release the full performance of MKL on the AMD processors, but on the latest downloads for MKL through the Intel's One API, the 20 dot versions of MKL, that environment variable has been taken away. So you do not get as good performance as you might expect out of MKL on the AMD processors. Yeah. So I hope that helps. If you use the Cray Python, it's linked down to libsci. So you should get the performance you'd get out of libsci through NumPy.
To answer Mike's question about, is there a disadvantage to using Conda if using, say, MPI for Pi in terms of performance? I don't think so. I haven't specifically run testing on this, but is there a specific reason you would expect there to be a performance disadvantage?
No, it's a question out of ignorance.
So the challenge of the Conda one would be, I think, Caoimhín, would be that it's not linked to the Cray MPI. You know, if you install MPI for Pi through Conda, you generally get a version of OpenMPI linked to sort of standard libraries for working on InfiniBand systems. Or now that might just work on Archer because Archer because sorry, on ARCHER2, because ARCHER2's interconnect is essentially Ethernet based. Underneath, it may be that the OpenMPI libraries that provide through Conda may just work, give the right performance. I think they'd certainly, almost certainly, give the right performance within a node. And whether you go over more than one node, it works. I don't know if we've tested that yet. I'm not aware of any tests of that yet, but it doesn't mean that somebody in the CSE team hasn't had a go at that to see if it works or not.
Okay.
But generally, I think our recommendation would be, if you want to use MPI for Pi, build on top of the Cray Python environment, because that MPI is linked through to the Cray MPI. That MPI for Pi is linked through to the Cray MPI and should work properly for you.
Okay.
I can see Louise asked about ASE and the atomic simulation environment. I think that is on ARCHER2. So these sort of things were really problematic on Archer, because what they did was they ran and then essentially used subprocess or something similar to launch, to do an MPI call out to a parallel program. Such as Louis says, Caster and WCAM. That should work better on ARCHER2, right? As long as you do not, you're not running the ASE itself in parallel. He said, thinking on his feet, then it should just work. If you do Python ASE.py or whatever the program happens to be called, then and the subprocess just does the srun castep.mpi or whatever it is, then that should work better. That should just work on ARCHER2, whereas it didn't work at all on Archer because of this, because of the way the ALPS parallel job launcher worked and subtleties in that. But that should just work on ARCHER2. Now, the thing that trips up, that may trip up quite a few packages or legacy packages, I don't know if ASE is one of them or not, which we have seen, is there's some things out there that are still only Python 2. And Python 2 is is deprecated now. So if you ask questions on Python 2, then the general response will be go and use Python 3. I mean, obviously we try to be a bit more helpful than that, but really Python 2 is just not supported anymore. I see Andrew asked another question about Python compilers, and there aren't any installed centrally on ARCHER2. I don't see why you shouldn't be able to install those sort of things yourself in your own space and use them to improve performance and build on top of the Cray Python installation.
Also, I think the service desk would probably be happy to help you do that if that were something you needed to do.
Yeah. If you run into problems, they just drop us a line, and we don't have any plans to make any of those things, any Python compilers available centrally right at the moment. And there's actually quite a long list of things to get through, and that one isn't high up on the priority list at the moment.
To answer Mike's question, can you run multiple srun Python commands in one job? Yes, you can. I think it's a simple answer to that.
There is complexity though, Mike. It depends what you want to do. Do you mean multiple multi-node sruns, or do you mean multiple, within just requiring a single node and then running multiple, say, 2-core Python jobs? Because actually the way you do that is different, and the case where you request multiple nodes and then want to use multiple sruns is a little more complex, because Slurm doesn't support the correct process pinning you have to be careful and use some tricks to get the explicit pinning correct. And it's in the documentation, but you do have to be careful.
Okay, thank you.
One thing that I guess that we haven't covered here, which may be useful to people if you're interested in Python more generally, and you're struggling to get packages installed on ARCHER2. The other way to approach this is to use containers. If you're really struggling to install something like this, ARCHER2, we've had some success with this, because sometimes it can be quite difficult to match up, for example, to the Linux OS version release for certain type of packages. Is if somebody's already built a Docker container, for example, with the Python environment you want in, the tool you want in, you can just singularity pull that Docker container straight from the Docker hub onto ARCHER2 and launch it as a container, and that may be short-circuiting any sorts of dependency issues or problems getting things installed using pip or conda. You can just go straight to the container and use that, and that might sometimes that might make it a bit quicker and make it a bit easier to get things up and running.
And that also feeds in nicely to the next webinar that we'll be hosting, which is on the 21st of April, so in 2 weeks' time, from 3 till 4 as well, where Michael Bereford will be talking about getting containers to work well on high-performance facilities such as ARCHER2. So given that there seems to be no more questions, I'll take this last opportunity to thank Caoimhín again for the very interesting talk. Thank Andy for some helping out with the answers, and thank everyone who's attended for coming. We hope to see you again at future webinars. I hope you all have a good day.